All right, the floor is yours. Have fun.
All right, we are at HeatSync. This is our progress report. Just to begin, to preface things, because we have 4 people, one of the largest groups, we split basically into 2 groups of 2, still working towards the same goal, but so we can tackle our research from different points of view. So the first few slides are Cam and Natalie's work, which they'll go over, and the last few are me and Brodsky's. And then, yeah, we can answer any questions or anything at the end.
So our parallel experiment here in simplicity is getting a PVC tube and running a copper pipe through it and stuffing the shell with a PCM composite, which is made of 15% expandable graphite, 3% borax, and then 4% SPA, which is sodium polyacrylate instead of the DSS. It's an alternative. And then 78% of Glauber salt, which is sodium sulfate decahydrate. And the salt is a phase change compound, so you run heat through it and it starts to melt, and then you can run a water line back through it and extract that heat. It's just basically like a heat battery, essentially. And we can measure the power and the heat absorption that it has using the flow rate of the water, which is our heat transfer fluid, and using the time it took to get from the temperature from the start to the end. We have to use the power. So far we've measured out our masses and our substances that we're going to use. So the total mass composite is going to be 1,250 grams. We already measured out 50 grams of the SPA, 37.5 grams of the borax, and then 187.5 expandable graphite, which we just got in, and 975 grams of the salt. And so our next steps are to create a pushing circle, or like a plunger, which has a flat end to push the substance down into the shell, but also has a hole in the middle to allow the copper pipe to run through the middle. And you're just compacting it down, and I'm pretty sure the density was 0.987 grams per milliliter.
Alright, there's a lot of elements to it. You want this?
Yeah. So what we've done so far is we tested the flow rate from that faucet using this flow meter here, you can see, to ensure that it was functional and that the threads actually matched with the faucet. And then we measured out the masses and volume of the tap water to get an accurate density. Since that tap water is not pure and it's not deionized, it actually has a heavier density than pure water, which has 1 at -4 degrees Celsius. And then we labeled all the substances with accurate masses and their names and their purities.
So that, yes.
Yeah, that's it.
Alright, so that's them. They're working on the heat storage battery with phase change materials. Me and Brodsky have been working on with thermoelectric generators, which we've been trying to place inside computers. You've probably seen like the Frankenstein deconstructed PC in the back. So we were testing the computer's ability to stay cool because we were placing a thermoelectric generator in between the CPU and the CPU cooler, which then allows it to generate electricity because it has one hot side and one cold side. And then with the Seebeck effect, it generates voltage. The problem is when you start sticking things in between the cooler and the thing that's cooling, it stops cooling as well. And so we've run into some issues with it overheating. We also have been measuring the power output from the thermoelectric generator compared to the temperature of the computer. You know, as the computer gets hotter, it's running more programs. It should be generating more electricity from the heat. So we've been testing that and measuring it with a multimeter. And then we use software like HWinfo to track the CPU temps. We have a nice graph of them compared to the voltages and currents that we measured, so that we can analyze the correlation and how that works.
All right. A lot of our time in
doing our experiment has been spent in rebuilding our little Franken computer back there. We've had to replace several components. We reinstalled a hard drive, we replaced the CMOS battery, we actually hardwired the fan directly to a variable power supply because we tried unsuccessfully to use softwares to tune the fan curves. Unfortunately, those fan curves are unlocked by Dell, by the BIOS settings, so we had to manually connect them to a power supply that we can control ourselves. And we are also working with rather old hardware, about as old as Hawthorne and I actually. And that has somewhat posed issues. The hard drive itself writes incredibly slowly compared to modern solid-state storage, and the processor is quite underpowered as well for modern standards, which has slowed a lot of download and configuration procedures. And we also invested a solid amount of time into thermocouples, which we were going to use for temperature monitoring on both the hot and the cold side of the TEG. But the main issue with the thermocouples is that they would not adapt quickly enough to temperature changes, which occur very quickly on a processor because of its very small thermal mass compared to the power it dissipates.
The bigger thing, I think, was we weren't getting accurate readings from the thermocouples because it's very delicate equipment and it requires that it uses electricity, and a computer has a lot of magnetic and electric fields running through it. So trying to get the thermocouple to work, there was a lot of interference basically, and we couldn't get a nice clean value that matched what we expected. It wasn't accurate, so we moved on from that. Okay, so far we've gotten, so for some of our problems that we've run into so far, we generated a lot less electricity than we were hoping to, getting 20 to 25 milliwatts, which is just enough to power one of the little LEDs over there. Now, based on similar experiments we've seen and from the calculations we did, we should be getting several watts. We're getting 0.6 volts at the max, I think, whereas we're seeing people get up to like 6 to 9 volts, and similar with current issues. So it could just be that we're using old hardware. Some of our thermoelectric generators are really old and they could be degrading, or it's possible that the experiments we're looking at online are just using better ones that have come out in more recent years. So we're looking to maybe get new thermoelectric generators, either buying them, or we talk on the next slide about potentially making our own in the lab, which will be one of our next experiments.
On the previous slide, we are looking at producing our own thermoelectric generators, particularly through electrospinning thermoelectric polymers onto a plate, which will produce a monolayer thin film thermoelectric generator, which in experimental studies have been shown to have incredibly high figures of merits, which it's basically a product of a couple characteristics of it, physical and also measured characteristics of the thermoelectric generator that characterize its effectiveness as a thermoelectric generator and its potential. And a lot of these studies have been very successful, especially in low temperature gradient thermoelectric generation, which is what we're looking at because nobody's personal computer is going to produce enough heat to create a several hundred degrees Celsius temperature gradient across a thermoelectric generator. One in particular I was looking at, I believe it was an antimony triphosphide, had like a 2.1 figure of merit at only a 41 degrees Celsius temperature gradient, which is very realistic for personal computer temperatures. And yeah, a lot of these procedures are doable with our lab equipment here, particularly the electrospinner for fabrication and our SEM for characterization and analysis. And so that's probably going to be our next experiment, our HO3.
For the first camera, your first experiment, you're running water through that copper tube,
Yes.
and then it'll be like kind of captured in the graphite stuff?
Yes.
Okay.
All right.